All right, let's go. Number 8, the Planck limit. For centuries, scientists assumed space and time were continuous. You could divide a meter in half, then half again, forever. Mathematically, there was no smallest distance. But modern physics disagrees. At approximately 1.6 times 10 to the negative 35 meters lies what is known as the Planck length. It emerges from combining three fundamental constants: the speed of light, the gravitational constant, and Planck's constant. At this scale, the known laws of physics stop functioning normally. Below this boundary, space-time may no longer behave like smooth geometry. Instead, it may become fundamentally discrete. Imagine zooming into a galaxy, millions of light years across, filled with rotating stars. Zoom further to a solar system, where gravity governs orbital mechanics across billions of kilometers. Zoom again to a planet, then to molecules, atoms, and subatomic particles. At each step, structure remains meaningful, until the Planck scale. At that depth, reached conceptually in about 10 to the negative 43 seconds of time, the Planck time, distance itself may lose definition. Quantum fluctuations of space-time become so violent that geometry collapses into uncertainty. There may be no smaller coordinates to describe, no deeper resolution. If true, the universe contains a maximum spatial pixel size, a smallest frame of time, and a fundamental limit on how finely reality can be rendered. In ordinary physics, such a boundary is deeply puzzling. Why should space-time stop dividing? Why should reality contain a smallest measurable unit? But in computational systems, limits like this are expected. Every simulation has a resolution, every grid has a smallest cell, and every rendered universe must eventually reach the smallest unit its engine can calculate.
Number 7, the black hole information paradox. In classical physics, information cannot be destroyed. This principle sits quietly beneath nearly every physical process we understand. When a star burns hydrogen into helium, the information describing its particles is not erased, it merely transforms. When planets collide or galaxies merge, the microscopic details of every particle remain encoded somewhere in the universe. But black holes threaten this role. When a massive star collapses, gravity compresses its core so violently that space-time folds inward. An event horizon forms, a boundary beyond which nothing, not even light, can escape. From the outside, everything that falls in appears permanently hidden. Matter disappears, light disappears, information appears lost. For decades, physicists believed this loss was acceptable. After all, the interior of a black hole was simply inaccessible. Then, in the 1970s, Stephen Hawking discovered something extraordinary. Quantum effects near the event horizon allow black holes to emit faint radiation, now known as Hawking radiation. This radiation slowly drains energy from the black hole. Over immense timescales, roughly 10 to the 67th years for a stellar mass black hole, the object evaporates entirely. And here, the paradox appears. Hawking radiation is thermal, random. It carries no information about what originally fell inside. If the black hole evaporates completely, the information describing every star, planet, and particle swallowed by it disappears forever. That would violate a core rule of quantum physics. As we scale upward, the consequences grow unsettling. Galaxies contain millions of black holes. Stars collapse into them. Matter cycles through them over cosmic time. If information is truly erased inside these objects, the universe itself slowly loses detail. But quantum theory insists information must always be preserved. So where does it go? One proposal suggests it is encoded on the event horizon itself, a concept called the holographic principle. According to this idea, all the information inside a region of space can be described by data stored on its boundary surface, a three-dimensional universe behaving as if its contents are stored on a two-dimensional surface. Not unlike how a video game world appears three-dimensional, while its data exists on a flat storage medium. If this principle is correct, then reality itself may operate like a projection, a volume of space rendered from information stored on a cosmic boundary. And black holes may not destroy information at all. They may simply compress it, like files being archived by the universe itself. Number 6, the Bekenstein bound. In everyday experience, space appears capable of holding unlimited detail. A room can contain furniture, air molecules, dust, photons, and an almost unimaginable number of microscopic interactions. Intuitively, there seems to be no strict upper limit to how much information a region of space can contain. But modern physics says otherwise. In the 1970s, physicist Jacob Bekenstein discovered something deeply counterintuitive while studying black hole thermodynamics. He realized that any physical system, no matter how complex, has a maximum amount of information it can store. This limit is now known as the Bekenstein bound. The rule is surprisingly strict. The maximum information inside a region of space does not scale with its volume, it scales with its surface area. Imagine a sphere 1 meter across. You might expect the information it can contain to depend on the number of particles inside the volume. Instead, the limit depends on the area of the sphere's outer boundary. Double the radius, and the information capacity increases with the surface, not the interior. This reverses our usual picture of physical storage. As we move across cosmic scales, the implications become more dramatic. A galaxy like the Milky Way contains hundreds of billions of stars, each with planetary systems, magnetic fields, nuclear reactions, and particle interactions occurring every second. Yet all the information describing that enormous system is still limited by the surface area of the region containing it. Zoom down to smaller scales. Stars forming from collapsing gas clouds over millions of years, planetary systems stabilizing over hundreds of millions, atoms forming chemical bonds in microseconds, and quantum particles interacting in fractions of a trillionth of a second. Every irreversible process increases entropy. Every event generates information. But the total information that can exist in a region remains capped. Reality, it seems, has a finite storage capacity. In an infinite, perfectly continuous universe, such a restriction is difficult to explain. Why should space itself limit information density? But in computational systems, limits like this are unavoidable. Every simulation runs on finite hardware. Every environment has memory constraints, and every digital universe must obey a maximum information budget. The Bekenstein bound suggests something unsettling. The universe may not be infinitely detailed. It may be operating with a fixed storage limit.
Number 5. The quantum randomness paradox. At the largest scales, the universe behaves predictably. Galaxies rotate under gravity. Stars evolve over millions to billions of years. Planetary systems stabilize through well-understood orbital mechanics. If you know the initial conditions precisely enough, classical physics can predict how these systems evolve far into the future. But when we descend into the microscopic world, this predictability disappears. In quantum mechanics, the exact outcome of certain events cannot be predicted at all. Not because our instruments are limited, not because we lock data, because the outcome literally does not exist until the measurement happens. A radioactive atom, for example, may decay in the next second, or remain stable for millions of years. Physics can describe the probability of decay, but it cannot determine the exact moment it will occur. This phenomenon lies at the heart of the quantum mechanics. Zoom down from a planetary environment to atomic structure. Inside atoms, electrons occupy probabilistic orbitals rather than fixed paths. At subatomic scales, particles interact through quantum fields, exchanging energy through discrete packets governed by Planck's constant. These interactions shape chemistry, which shapes planetary atmospheres, which ultimately shapes biology. Over billions of years, microscopic randomness can cascade upward into macroscopic consequences. A single quantum event can influence molecular structures, cellular mutations, ecological shifts, and eventually entire evolutionary paths on a planet. The chain is irreversible. Entropy increases. Information spreads. Yet the initiating event remains fundamentally unpredictable. This randomness poses a deep paradox. If the universe is governed by deterministic physical laws, where does true randomness come from? One interpretation suggests the universe is inherently probabilistic. Another, known as the many worlds interpretation, proposes that every possible outcome actually occurs in separate branching universes. But there is another possibility that some physicists have quietly considered. In complex computational systems, randomness is often introduced deliberately. Simulations frequently rely on random number generators to determine outcomes that cannot be calculated deterministically in real time. Not because the system locks rules, but because randomness is computationally efficient. Quantum randomness behaves in a strangely similar way. Outcomes are not calculated in advance. They are generated at the moment observation forces the system to resolve. In other words, reality may not be fully computed until it is observed. Number 4. The speed of light bottleneck. Across the universe, nothing travels faster than light. This limit, about 299,792 kilometers per second, appears in every successful physical theory we have. Information, energy, and causal influence cannot exceed it. No signal, no particle, no gravitational change can propagate faster. This rule lies at the center of special relativity, first formulated by Albert Einstein. But the speed of light is not simply a fast speed. It is the maximum possible speed. And that is what makes it strange. Imagine the universe on its largest scales. Galaxies stretch across millions of light years. Clusters of galaxies form vast gravitational webs spanning hundreds of millions of light years. Light itself takes billions of years to cross the observable cosmos. Yet, even at the smallest scales, inside atoms and quantum fields, interactions still respect the same limit. If a star explodes in a distant galaxy, the information about that explosion cannot reach us faster than light. Even gravity changes propagate at that speed. If the sun vanished instantly, Earth would continue orbiting for about 8 minutes before noticing. Cause and effect are delayed, everywhere, across every scale. From collapsing stars to particle collisions lasting less than a trillionth of a second, information always travels through spacetime at this fixed rate. In ordinary physical reasoning, this raises a difficult question. Why should the universe enforce a universal bandwidth limit? Why should information propagation have a maximum speed at all? If space were a perfectly continuous medium, influences could theoretically travel arbitrarily fast. Yet nature imposes a strict cap. In computational systems, however, such limits are common. Large simulations cannot update every region of a virtual environment instantly. Information must propagate across the system step by step, frame by frame. Updates spread through the grid at finite speeds. Otherwise, the system would require infinite computational power. The speed of light functions in a strangely similar way. It acts like the maximum rate at which the universe can transmit information across its own structure. A cosmic latency limit. A rule that ensures no region of reality updates faster than the underlying system can process. Number 3, the cosmic horizon problem. When we observe the universe on its largest scales, we see something remarkably uniform. In every direction, space is filled with faint microwave radiation, the leftover heat from the early universe. This radiation is known as the cosmic microwave background, first detected by Arno Penzias and Robert Wilson in 1965. It represents light released about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons could finally travel freely. What makes this radiation strange is how uniform it is. No matter where we look in the sky, the temperature differs by less than 1 part in 100,000. Regions separated by tens of billions of light years appear almost perfectly synchronized. But according to the laws of physics, they should never have communicated. Light travels at a finite speed. In the early universe, distant regions were too far apart for any signal to travel between them before the cosmic microwave background was emitted. These regions were outside each other's causal horizon. They had no way to exchange energy, no way to equalize temperature. Yet somehow they ended up nearly identical. This contradiction is known as the horizon problem. The leading explanation involves a brief but dramatic event called cosmic inflation. During the first tiny fraction of a second, around 10 to the negative 36 to 10 to the negative 32 seconds after the Big Bang, the universe expanded exponentially, stretching a tiny, uniform region into the enormous cosmos we see today. Inflation solves the mathematics, but it introduces its own mysteries. What triggered this expansion? Why did it stop? And why were the initial conditions so perfectly tuned? Zooming across scales makes the tension clearer. Galaxy clusters separated by billions of light years today share nearly identical early conditions. Those conditions shaped the formation of stars, planetary systems, and ultimately the chemical environments that allow life to emerge. A small patch of early spacetime somehow determined the structure of the entire observable universe. In simulations, this kind of large-scale uniformity often emerges from a simple starting grid. A single initialized state spreads outward as the simulation expands, and every distant region inherits the same starting conditions. In the real universe, the horizon problem leaves us with a similar question. Why does the entire cosmos appear to have been initialized all at once? Number 2, the fine-tuning paradox. The universe is governed by a small set of fundamental constants.
These numbers determine how strongly forces interact, how particles behave, and how matter organizes across every scale of reality. They include quantities like the gravitational constant, the strength of electromagnetism, and the masses of fundamental particles. At first glance, they appear arbitrary, but when physicists began calculating how sensitive the universe is to these numbers, something astonishing emerged. Small changes, sometimes by fractions of a percent, would erase the possibility of structure entirely. If gravity were slightly stronger, stars would burn through their nuclear fuel in a few million years instead of billions. Galaxies would collapse rapidly into dense clusters of black holes. If gravity were weaker, gas clouds might never collapse into stars at all. The strength of electromagnetism determines how atoms bind together. Change it slightly, and stable chemistry becomes impossible. Molecules cannot form. Planets cannot accumulate complex materials. The masses of subatomic particles also sit within narrow ranges. If the proton were slightly heavier relative to the electron, atomic stability would collapse. Hydrogen, the simplest and most abundant element, would not exist. Without hydrogen, stars could not ignite nuclear fusion. Without fusion, heavier elements like carbon, oxygen, and iron would never be forged inside stellar cores. Across cosmic time, over billions of years, these processes produce planetary systems, chemical complexity, and eventually biology. The chain stretches from quantum fields to living ecosystems, and every step depends on precise numerical values embedded in the fabric of physics. This phenomenon is often called the fine-tuned universe. Some physicists argue the explanation lies in the multiverse, a vast landscape of universes with different constants where ours simply happens to permit life. But another perspective raises a different possibility. In engineered systems, constants are rarely accidental. They are parameters, numbers chosen carefully because they produce stable behavior inside the system being modeled. A simulation designed to generate complex structures would require similarly narrow conditions. Gravity strong enough to form stars, electromagnetism tuned for chemistry, particle masses calibrated for stable atoms. The fine-tuning paradox does not prove the universe was designed, but it reveals something difficult to ignore. Reality appears balanced on a razor's edge of numerical stability. At the deepest level of modern physics, the universe is not built from particles. It is built from fields. Every particle we observe, electrons, quarks, photons, is simply a localized vibration within an underlying quantum field. These fields fill all of space, even what we call empty vacuum. In this framework, the vacuum itself is not nothing. It is the lowest energy configuration of these fields. But there is a disturbing possibility hidden inside the mathematics of quantum field theory. The vacuum we occupy may not be the true lowest energy state. It may only be metastable. This idea emerged from detailed measurements of the Higgs field, discovered experimentally at CERN in 2012. The mass of the Higgs boson appears to place our universe in a delicate region between absolute stability and eventual decay. If the calculations are correct, the vacuum could theoretically transition into a lower energy state. This process is called vacuum decay. The mechanism is brutally simple. Somewhere in spacetime, a tiny quantum fluctuation could trigger the formation of a bubble of lower energy vacuum. Once formed, that bubble would expand outward at nearly the speed of light. Inside it, the fundamental constants of nature would change. Particle masses would shift, forces would behave differently, atoms could not exist, stars would never ignite, chemistry would vanish. The bubble would sweep through galaxies, stars, planets, and atoms without warning. Because it expands at near light speed, no signal could outrun it. No observer would ever see it coming. From the scale of galaxy clusters down to atomic nuclei, the entire structure of reality would simply cease to be compatible with its own laws. The unsettling part is not the destruction, it is the implication. Our universe appears to be balanced in a delicate configuration of its quantum fields, stable enough to last billions of years, but potentially not the final state of reality. In ordinary physics, such delicate metastability is unusual for a system as vast as the universe. But in computational systems, unstable states are common. They occur when a system is initialized in a local energy minimum rather than the global one, stable for long periods but not permanently. A simulation can run perfectly for billions of steps while still sitting in a configuration that could collapse if a certain threshold is crossed. The vacuum instability paradox suggests something equally strange.
the entire universe may exist inside a temporary configuration of its underlying fields, a state that works, a state that produces stars, galaxies, chemistry, and observers, but not necessarily the ultimate ground state of reality. Which means the laws we experience might not be the deepest layer of existence. They might simply be the parameters of the current run. Across billions of years, the universe has produced galaxies, stars, planets, and the fragile chemistry that eventually gave rise to conscious observers. Yet the deeper physics we uncover continues to reveal limits, boundaries on information, speed, resolution, and stability. Whether these are simply the natural properties of reality or hints of something deeper remains an open question. What we know for certain is this: we exist during a rare moment in cosmic history, long after the first stars ignited, yet long before the universe grows dark and cold. A brief era where the universe is complex enough to be understood, and where it has produced minds capable of asking what it truly is.